Welcome to a discussion with Etash Guha regarding his paper Conformal Prediction via Regression-as-Classification. As usual, you can find links to the paper and other references in the description. And with that being said, let's jump into it. Would you mind providing some background for the paper, why you
Yeah,
chose to write it, also the collaboration group that was kind of put together to investigate this?
yeah. So I've been working on conformal prediction for a little while. So the idea of conformal prediction is actually really simple at its core. The main idea is, let's say we're doing some classification or regression problem, and we don't want to just simply output a single output. Our ML algorithm we may want to quantify uncertainty in some way, and that we have a set of outputs that we're pretty sure has the right answer in there. So for example, let's say we're doing classification in like a recommendation system for Amazon. They may want to, instead of like outputting the best possible like fit for a product, it may give you a set of products that are likely to contain what the user wants. So there's like a lot of use cases for conformal prediction. So conformal prediction is just one methodology of outputting that set. The issue is using conformal prediction for classification is pretty well known how to do it, and it works really well in practice. For regression, so when you have to input like an interval of numbers, it's a lot harder. The methods get very complicated very quickly. And I'd done a paper before on using conformal prediction to do regression, but the answer to that problem was kind of slow, the algorithm, and certainly wasn't optimal. So it return very large sets. So like a very easy way to do for prediction would be just return the whole output space. So like if you're predicting a you're trying to predict a student's grade on a test, you could obviously output 0 to 100 and you're going to be right. But
Mm-hmm.
that's pretty useless. And so what I wanted to do was, which people have been in this field have been trying to do, is finding a methodology that's both quick and tight. So it means it gives intervals that are very close around the true answer while maintaining coverage. So coverage means like you do contain the true answer a good amount of the time.
Mm-hmm.
And so what this paper came from, I was doing an internship at Riken, which is a lab in Japan, and me and my advisor, MTOS, who's on this paper, and Eugene was a former collaborator of mine on a couple other CP papers. I had the idea of really simplifying this process for regression. I really wanted to try a way more general approach for solving these things, and I wanted to use some like very basic probability estimation systems that have been used since like the 90s. I thought like these very fancy techniques that we've been using for prediction they work, but can we try simpler, which would hopefully get better results? So when I was at Recon, I wanted to try this approach, and this kind of came from that. So this is using some very simple approaches for that have been used since like the 90s and using that for conformal prediction.
Mm-hmm. Okay, just to reiterate on the output of these kind of systems. So you mentioned that we could either have like a point estimate that we're trying to get. So you feed it one specific point, and then you want either one one result or maybe a set of results if we're talking about a recommendation engine like Amazon. In terms of the actual output for this system, are you generally looking to get a probability density over a set of potential
So
states, or are you looking to somehow get boundaries? Like what is generally speaking the setting that you apply this to?
yeah, so for this paper, it's regression only. Like this paper is conformal prediction for regression, and the
Mm-hmm.
output is an interval. Like just like some sort of continuous interval over the output space.
Right.
So if we're in the setting of grades, it'll be like I think the student's going to get between an 80 and 85.
Mm-hmm.
That'd be
I
the
mean,
output.
maybe we can pull these up as well for kind of an introduction.
Yeah, yeah. So you can see here, like for this example, let's say we have we only get to know one bit of information about the student. Let's say their age, and we're trying to predict their performance on a test. And let's say that x-axis is age. I know it's not normalized, but let's imagine it's age. Well, for example, for an age of -1/2, like give or take, right? The output of the algorithm have been, okay, I think this person is going to get between a -0.5 on their score and a 1 on their test. right? So that's the output of the ML algorithm. So it could these intervals don't need to be continuous. For example, like you can see for if the student has a age of 1, like on which is like the normalized age, they think the algorithm thinks it's going to get between like -2, -1, so it'll do really bad, or either do really good, between 1 and 2, but it doesn't think it'll get in between. So like these intervals don't need to be specifically continuous. They just need to be roughly intervals. There's intervals in general. So any
Okay.
intervals really is the answer to CP.
Okay. Could you talk a little bit about conformity score? Because I guess that's
Yeah,
where we will eventually be heading with this. So would you mind introducing that concept in general, and then we can talk about some common conformity scores that are out there and that people tend to use?
yeah, exactly. So for those who aren't familiar with CP, the whole crux of conformal prediction was written by like Wolf and Schaffer in the early thousands, maybe late 90s, you could argue, about it's a very simple system that relies on one simple aspect. So it relies on something called a conformity score, which given some input X and some candidate output Y, it estimates how good of like how likely of an answer that is. Likely is not probably the best term, but like how good of an answer that is. So for example, if I have a student and I'm trying to predict like a grade for that student, let's say they're a very, very good student and their features about the student are very, very good. The conformity score should say, okay, if I take this student's features, which is we'll call X for now, and a grade, like a potential grade, like Y, let's say that, for example, our grade is 10. And the conformity score should be like very, very low for that combination of input and candidate score, right? Because it's very unlikely that student's going to get a 10. Or it should be really high, for example, for still like 90 or 95. So, and it should be the inverse of like the student's really bad. Let's say the student's a really bad student. The conformity score should be really high when you combine like on an input of that really bad students and features, and the candidate score is very low. So it basically just estimates how good a candidate output is for a given features, and how good your conformity score is. It basically determines how good your intervals are going to be. So how good your CP algorithm is going to be. So for example, a conformity score that is very, very random, that has like basically no information, will give you very, very, very loose intervals. It'll give you intervals that basically don't contain any information. It'll be like, I think the student's going to get a grade between 10 and 90, right? It's going to not can tell you anything. But if you have a very, very accurate score, let's say your score is perfect. It actually can predict exactly when the student is going to get what the student's going to get on their exam. Your intervals will be super, super small. It'll give you very, very good estimates naturally. And so the whole game of CP is, can we figure out how to estimate conformity efficiently that generates tighter intervals? So how can we, there are like super fancy techniques for getting this. There's very simple techniques for getting this. So balancing efficiency of your algorithm versus the accuracy, that's a classic ML problem. That's kind of the name of the game for conformal prediction, and it's quite a bit harder in a regression setting. So in a regression setting, there's infinite amount of outputs, right? In the classification setting, there's a set amount of outputs, so there's a finite amount of outputs, so you can kind of do other things that work. But for regression, you can't just iterate through every possible output and figure out, like, do some estimation. You can't do that. So how do you do that in the regression setting? That's kind of the problem here.
In the regression setting specifically, are there any methods right now that are dominating the space of applications?
Yeah.
So if you're talking about like Amazon and these players, are they all relying on the same kind of methodologies for this, or is there a large variation?
Yeah, so there is a good amount of variation, but I think in the last few years, a couple, like very few methods have dominated. So there's a couple of papers, namely conformalized quantile regression and conformalized histogram regression by the same set of, like roughly same set of authors. I believe Emmanuel Candace is on both. He's a professor out of Stanford who's really been working really hard on conformal prediction, and his group is. And they've outputted some really great work. Namely, I think the biggest paper in the space is conformalized quantile regression. And basically what they do is their conformity score is for a given output X, let's say the student, it tries to predict the 25th percentile quantile of their grade and the 75th percentile quantile of their grade. Or I think it was maybe 10th and 90th percent quantile of the grade. So like it thinks if it's like there's a 10% chance that a student will get like an 85 and a 90% chance, like the 90 percentile of their grade is probably like a 99. It just estimates how far you're from those quantiles. That's your score.
Mhm.
And it may seem a bit contrived, right? And that's kind of the approach I have. I'm like, that sounds, it makes sense, right? How far you are from those quantiles. Like if you're dead in the middle of those quantiles, that's probably, you're in the 50th percentile, that's a good estimate. But if you're very far from those quantiles, it's a bad score. Like you're very outside those quantiles, bad score.
Mhm. Yeah.
And it seems a bit contrived, but it's simple and people have used it and it works pretty well. So that method kind of has dominated. I think they did a sequel to that paper. I don't know if you would classify it as a sequel, but rather they did a follow-up. And it's called Conformalized Histogram Regression, which is somewhat similar to this paper in the fact that they try to estimate a histogram of the distribution of the answers, of like a histogram over the output space. There's like any
Mhm.
random histogram, and your conformity score is how high is the bar at your given like at your y. So they try to estimate what a histogram for that distribution for a given x would be, and your output, your conformity score is just what that histogram says, that like the frequency of that histogram.
Mhm.
So those two methods kind of dominate. The issue that not the issue, they're great papers and they work really well. I wanted something that was a bit simpler. Like the quantile thing makes sense intuitively, but this seems like a little contrived. That works. That should be the best. I don't. To me, that didn't seem like there was a fundamental reason why distance from quantiles and this like pinball loss. So like basically, if you look at the graph of like the conformity score given to quantiles, it just looks like a little pinball thing. So it's like the y if it's really here, and maybe you could even bring that paper up, for example. But that if you look up the pinball loss score, like
We can at least link it. I don't know if you have a figure. I mean, I can pull it up as well, so we can look at it on the screen. But I
yeah, I
don't
mean
have it open at the
we can
moment.
bring it up if you want to. Like there's a figure in there, like I don't know what page it's on, but it says it's like the pinball loss figure.
Okay, which paper do you want me to pull up?
Just look up conformalized quantile regression. There you go. That's it.
Oh,
That's
okay,
it.
this one.
Yep. So that's
Okay.
their kind of their conformity score, right? So given some candidate Z, that's their output. You can think of it like Y, whatever.
Mhm.
Uh, Distance from the quantiles is the is like that Z value. So like how far you are from your quantiles.
Mhm.
That's a graph the conformity score. Makes sense, right? If you're exactly on like the middle of the quantiles, you get it's a very good score. But if it's like very far away, you have a very like low score. Like it makes
Mhm.
sense. But it
Okay.
seems a bit contrived to me. I didn't seem like this is some fundamental reason that this should be the perfect method. And
Mhm.
so I wanted to do something a bit more fundamental. I think something more like simple and
Yeah.
less that is makes more intuitive sense to me personally.
Mhm.
And so
Well,
yeah,
if we switch back to the paper, I guess, or to the first paper,
yeah,
I guess we would have some issues in circumstances where we have, for example, bimodal distributions, right?
yeah. So this paper
So,
actually can't do bimodal distributions.
right. Oh, actually, I'm not sharing the. Wait, let me share the original paper again. Um,
Yeah, so that's
I
actually
thought
really
I
interesting.
could. Yeah.
If you give
Right.
it bimodal, yeah, good.
Right. So if we look at this one, I guess this one it would struggle with, for example, if we
Yeah, it
would
could
feed
not
it.
do that. That's why we have this as an example. Like this paper, the CQR paper on like an input when x is like 1.5, will return an error between 2 and like -2. So, and in our experiments, we confirmed this. It really is very poor at bimodal distributions just by its fundamental. It just can't compute bimodal. It can't take advantage of that.
Mhm. Okay. Would you mind giving an overview of your approach and the reason why, the fundamental reason why it's able to handle these kind of situations?
Yeah. So in our paper, we wanted to like the very simple, I think the most obvious conformity score for me was what's the probability of y given x, right? That's like a very fundamental idea to me, right? A y, a candidate label y is good if p of y given x is high. Like the probability of y given x is high, and it's a bad score if probability of y given x is low, right?
Mhm.
I mean, to me that makes the most sense. I don't know about to you, but that seems like the most simple answer. The issue
Mhm.
is how do you compute that density function? So given some
Right.
training data, how do you estimate that function? And so, I mean, estimating py given x is like given some training data is like the classic ML problem. There's so many. There's billions of papers on it. And in the regression setting, there's a lot that do this. For example, there's a paper called Conformal Bayes, which they use Bayesian methods to estimate this py given x, right? And so we do the same thing. We just want to estimate py given x. The thing we notice is if you look back into the literature of conformal prediction, and as I mentioned, for classification, what people have done for CP is actually really simple. You train a classifier on your labels, right? You train on your training data, and P of Y given X is just the logit of that output. So if you have like 10, you're doing MNIST, and you can just train a neural network that has 10 output nodes on your neural network, and the probability of like a given label is just the softmax probability scores, right, of your neural network.
Mhm.
That's what people do for ML for years, right, for classification problems. And it turns out like using that very simple method works. It works great for conformal prediction, and it's very natural, right? It's very simple, very natural. But in regression, you can't do that, right? Because there's an infinite amount of labels. And I, I thought like there really shouldn't be such a different. We shouldn't really tackle these problems so differently, right? Was like in my heart of hearts, regression and classification they shouldn't be such a different problem. So I
Mhm.
was like like just on a rhyme like, what if we just made the regression problem a classification problem, right? We just discretized the output space, made each bin like we into like 50 bins or 20 bins, and each bin is
Mhm.
now a class, and now we're doing just it's just we can just reuse classification CP. That is the whole paper. That is exactly what that is. We say, okay, let's just transform this problem into something we know how to solve, which is classification CP, and use
Mhm.
simple classification CP techniques. That's the paper. It
Mhm.
works. It works pretty well in our experiments, and it's very simple.
Mhm.
So exactly what we do is we take the output space, turn it into like 40, 50 bins, and we did experiments where we did like number of bins. It doesn't really make a difference as long as you have a sufficient number of bins. Um,
Mhm.
we train a neural network that to place like to on this new on this training data set. So it's like a classification data, like training data set now. We return the trained data set into something in classification. We do a little bit of a different loss function. So I mean, you could do cross entropy, but we do something very similar to cross entropy, but we add some like regularization. So people do like we do something called entropic regularization. I can
Mhm.
explain what that is in great detail a bit later, but people have done it for a long time. It's not like something new, novel to this paper.
Mhm.
When people like estimate probability distributions, people you do like regularization, which is like entropic regularization. But
Mhm.
sufficient to be said, we learn a probability distribution over the bins or like the classes now, and we use that probability distribution to inform as a conformity score, and we do CP like the classic CP method on top of it. Works like a charm.
Mhm. Good. So I just pulled up in the meanwhile the
Mhm.
summary of sort of your approach here, and I think it would be interesting to talk a little bit more about the loss function and the fact that in turning this into a labeling problem, essentially, you're losing the intrinsic order between the buckets that you're trying to
Yeah.
assign
Yeah.
a observation to. So could you elaborate maybe on how those two are related and how that infers your choice of loss function? Because I take it that the choice of loss function in this particular case is a way to get around that particular problem.
Yeah, exactly. So the classic technique, right? The simplest thing when you do regression classification is using cross entropy loss, right? That's what everyone
Mhm.
uses. But yeah, so cross entropy loss doesn't take into factor like some bins are closer to each other, right? So the bin, if we're doing grades, right? The bin for like grades 20 to 30 is and the bin for 30 to 40 are they're pretty close, right? And so the probability like if a student is likely to be in the 20 to 30 range, it's probably not a crazy thing that they should also be high in the 30 to 40 range. It's not so bad if we guess they're in the 30 to 40 range. But if we guess they're in the 90 to 100 range, that's really bad.
Mm-hmm.
And all this loss function does is it penalizes the amount of probability you put in bins that are the farther away from the truth you are, the true bin, the worse your penalty is. So you can see like the L. So Q, I can explain like the notation. So Q of theta is like the probability distribution outputted by our network. X is like some given feature, so like an input training data, training feature, and Y Y hat is like the bin we think it is, like the bin, like the like for an example bin, right? And so Q theta of Y hat is the probability we put assigned to that bin. And so, for example, if that and that L Y I Y hat is like the distance between the two bins. So the loss function is just we sum over all the bins the probability of that bin that we assign to that bin times the distance to that bin. And so if we assign really high probability to bins that are very far apart, our loss is going to be really high. If we assign really low probability to bins that are really far away and really high probability to bins that are very close, our loss function is going to be very slow, very low.
Are there any applications of this where the distance, the quote unquote distance between the bins is not as clear? So obviously, if we're doing a regression problem akin to the ones that we were looking at in the graph, it's pretty straightforward. You have a one-dimensional line essentially that you're trying to split up into different intervals, and then the distance between those is very clear. Do you also have more high-dimensional settings where that the distance you want to assign is not always evident?
Yeah, so that's a great question. Actually, one of our reviewers for the paper had this very question: how do you apply this method in multidimensionality settings?
Okay.
And conformal prediction for multidimensional regression is a hard problem. In this paper, we don't have a good solution to it. We don't know how this method will work at high dimensional settings. We don't know what distance function works best there. So if you can look here, like our distance function is really similar. We take the midpoint of the bin, subtract them, find the absolute value of that, and put it to the power of p. P is just a hyperparameter, right? It could be 1, it could be 2, whatever. I do not know what is the right parameterization in the multidimensional regression setting. I don't even know how you would do CP as an algorithm in the regression setting efficiently. So when you do CP in like multi-dimensions, the scale is really bad with dimensionality. So like the complexity algorithm, so people just don't do it. I've seen some papers that try it, but I don't know. We're not there yet as a field. So this paper does not solve that problem.
What would the multidimensional setting translate to? So I'm thinking in terms of what we said in the beginning. We have, for example, companies like Amazon that would like to give you predictions. Don't you have problems in that sphere where you run into wanting to classify this in a multidimensional setting? And if so, what are kind of the common ways of getting around that? I'm struggling now, so maybe you can help me with this, but I'm struggling to conceptually get a feel for what that high dimensional problem would map onto in the real world, so to speak.
Yeah, so let's say a multidimensional regression problem. I'll keep to the grade setting. Let's say we're not only trying to estimate a student's grade, but we're also trying to estimate the amount of time they spend on their homework.
Okay, so right, so the dimensionality is simply linked to the amount of predictors that you have, or the amount of quantities you're trying to predict.
Yeah, exactly. That's
fine.
that's exactly it. So maybe like then these things are correlated, right? If a student spend a lot of time on their homework, they're probably gonna have higher grades. And if they don't spend a lot of time on their homework, they're gonna have lower grades. So there's some correlation here. So simply like you could devolve this into 2 regression problems. Like you just try to estimate the student's grades and then try to estimate the amount of time they spend on their homework, and then take these 2 sets and just kind of do like a cross on them, just but that's probably not the best way because these things aren't independent quantities. And so you could, if you're doing multi-dimensional regression, you could you want to do this more in a controlled way. So you want to kind of learn the correlation. So you may, for example, like train a neural network where not you don't have just like k bins. So like let's say another thing we just separate everything to 50 bins, right? For
Mhm.
like the output space for grades. So say like or 10 bins, for example, for 0 to 10, 10, 20 for a grade. We could also make we could do all combinations of bin for grades and bin for amount of hours spent on this, like a thing on their homework. So it could
Mhm.
be we could predict the probability of they get a grade of 0 to 10 on their test and they got spent 20 minutes on the homework. We can predict the probability of they're going to get a 10 to 20 on their test and they spent 2 hours on the homework, right? So there's going to be if there's we do k bins for the number of grading, like bins for grading, and we do k bins for the number of like hours spent on their homework. That's k square output spaces, right?
Right.
And I mean, so the amount the amount of output bins that you have, like outputs for your neural network, is going to be k to the power d. So
Mhm.
if you have like a 20-dimensional regression problem, that's a lot of outputs, and it gets really,
Right.
really like, I guess it gets really noisy really quickly.
Mhm.
So doing multidimensional regression is a hard. At the end of the day, all I'm saying is a hard problem. There are probably yes a lot of real world applications. I do not know how you would do CP efficiently there. I thought about it a little bit. It is not an easy problem.
Mhm. Okay. Let's say a couple of words about the network as well that you're using here. So, could you elaborate a little bit on the architecture of that and why you went ahead with the kind of architecture that you did? What's the
Yeah,
important characteristics?
the I wanted to just be as simple as possible, and the simplest network was just a simple softmax classification network, right? This is a neural network with like I think 3 layers, ReLU activation, and has k output nodes, like k output. That's it. It's just as simple as it gets. Really, I
Mhm.
wanted to. I think that's the thing people have been doing for a long time. Just keep it simple.
Right.
That's it. And we hope by keeping it simple, it's more generally applicable.
Does that generalize sufficiently well to the kind of evaluations you ran this model on? So maybe we can
Yeah.
start looking at the results a little bit, but
Yeah.
the network is not very deep and there's not that many parameters in it. So does it generalize well, or did you observe in the results some settings where it didn't?
Yeah. So, I mean, for a bigger data set, a bigger network was better. We kind of kept the same network for all of our experiments to keep it simple, but we just chose like a decently big network that had a decent amount of parameters. We didn't really iterate too much on the architecture because we thought that would defeat the purpose. We wanted this to be more we by iterating on the network, I think that kind of defeats the simplicity of this approach. You want this to be a very general, simple method, and so
Mhm.
hopefully this would scale across a bunch of different networks and like sizes. So we just picked a very simple, big network that worked well for our data sets. Um, Probably if you're trying to do this for like very, very large, like sentiment classification for like things, you may want a bigger network.
Mhm.
But for our data sets, like our regression data sets, the network size we chose was fine.
Okay, cool. Let's have a look at the algorithm. If there's anything you think ought to be said about this, because after that, I would suggest we move to the results. But is there anything you think is worth highlighting when it comes to?
Um, so our method of CP is something called split CP.
Yeah.
So there's a kind of two camps for conformal prediction, and camps that I don't mean like they play against each other. There's just like two forms, split and full conformal prediction. And suffice it to be said, split means you just take your training data and you section off a little bit for calibration. And what you do in your calibration is like you basically calculate conformity. You just see like the range of your conformity scores across like a bunch of your calibration set. So you train your network Q with theta on your training data set, and then when you're trying to like see whether something is a good candidate solution, you look at how does my conformity score look across my calibration data set? Like, does it give me very high probabilities or very low probabilities? I mean, we can just see how it is relative to the calibration data set. It probably is not the best for me to explain split CP here. So if you're interested, you should probably go look at it. There's plenty of resources. But because split CP is this probably wouldn't be the best place to give a conformal prediction lecture. But split CP
Right.
is a very simple, very practical method of conformal prediction. That's the big thing I would note here.
Okay, very good. So then let's start talking about the results. I think table
Yeah.
one is maybe where we can start. So we
Yep.
have a comparison in table one with the solution we just described, and then a number of baselines. Could you
Yeah.
elaborate on what the most important baselines are, and some of the results that we see in this
Yeah,
table?
let me quickly go over what these results and metrics these are. So
Yeah.
there's two metrics in CP: coverage and length. So coverage is the amount of times you can contain the true answer, and length, which is like how wide your intervals are. So obviously, if you give the length the entire output space, like grade 0 to 100, you're gonna have 100% coverage.
Mhm.
But you don't want that. So what CP does is, and there's a beautiful proof of this, is that if you specify coverage as a hyperparameter in your CP algorithm, you can guarantee with high probability you're going to get that coverage. So all these sets and all these methods get 90% coverage because we set that as a parameter of our algorithm. Why that works, and you should look into the proof. It's a beautiful two-liner. But basically, all of these sets and all these methods get the same coverage guarantee. They're all going to contain the true answer 90% of the time. So that's fixed. And we include empirical verification of that in the appendix. But here, these are the length of those outputted sets. So how short or how small are those intervals, and how informative are they? And so I would say the biggest baselines here are CQR and CHR. So CQR is the paper we just looked at, conformalized control regression, and CHR is conformalized histogram regression. So like kind of the follow-up that I mentioned.
Right.
And I think CHR and CQR are people kind of assume are like the best in the field. And by no means do I say this paper is the best across every data set. And you can see like for a lot of data sets, sometimes it's CQR, sometimes it's conformal Bayes, which is CB there. But across most of the data sets, our methodology gets the best intervals.
Mhm.
And so
Are
for
there
some,
any other baselines here that also handle, for example, bimodal distributions?
yeah, so CHR actually does not. In theory, they can, but they do a little bit of post-processing. KDE does, so kernel density estimation. That does.
Mhm.
So it basically just approximates the probability of y given x using some sort of kernel methodology.
Mhm.
And they can do bimodal, and so you can see under the bimodal one, they're actually the best.
Right.
So us
And they
and
seem to be the only ones besides yours that are actually able to deal with it in the set
yeah,
of baselines.
the other methodologies put in some assumptions to make such that they can't handle bimodal distributions.
Mm.
So KDE does, but we replaced basically the KDE is very similar to our methodology, except they use kernels, we use neural networks. So,
Right.
and we do a couple other things that are different, but we're just more modern.
Mhm. Okay. Anything else regarding this table that you think is worth highlighting?
Um, I don't think so. I mean, the results are kind of simple. They kind of speak for themselves. It works pretty well. It works across a lot of different data sets. Maybe it doesn't get you the best performance a lot of time, but usually it's not going to like fail you too much.
Mhm. Okay. I think there's an accompanying figure to this one, which is in the appendix, figure 6. Maybe we can have a quick look at that one because it contains also graphs of some of the examples, right?
Yeah. Yeah.
Here we go. Okay, this one. So I don't
Yeah.
know if there are any of these that you think are worth
Oh yeah.
pointing out. I think there was a comment on the bimodal here, for example, somewhere in the paper. But yeah, if there's anything you think is worth highlighting here.
Yeah, for sure. So, and for context, what these figures are is the outputted probability distribution of our method, right? So, give us some example x. What is the probability distribution over the outputs y? And so, I think the key thing here is that these distributions are not that is learning aren't simple. Like they're kind of weird, they're kind of jagged, but they're very interesting. So for our bimodal, it's kind of fun, right? It's actually this learning a bimodal distribution.
Mm.
The and for each one of them is learning like different distributions. So I thought that was really cool, and it's actually taking advantage of the ability to learn very general distributions, right? So in the previous works, like conformal Bayes, for example, they kind of prescribe a posterior distribution. So their distribution can take a very specific shape.
Mhm.
But we don't want to do that. We want to learn our distribution. And it's doing that very thing, right? It's learning very different distributions for each data set, for each example, and is able to really take advantage of the fact that it's a general method. It can learn very general distributions. And if you scroll up for like
Mhm.
MEPS, for example, it's super long tailed and is able to take advantage of that. For
Right.
bimodal, it has those two like modes. For bio, it's kind of long tail, but not too bad, right? So I think that was a cool part about this. You kind of learn very general distributions.
Hmm. Yeah, I guess situations like these are kind of hard to replicate with the other techniques, especially if they assign a posterior, right?
Yeah, so
Um,
those methods won't do as well. I mean, some methods do fine, like CQR does fine. I don't remember the exact number. So CQR does fine. I think C CHR also does fine. But across all of them, like some of them, if the more assumptions you put in place, the more rigid your distributions are going to be.
mhm. Okay, good. So let's go back to the results then, and we can maybe look at the second table associated with this as well.
Yep.
Um, okay, here we go. Would you mind describing what you're actually attempting to do here, if you can paint the
Yeah,
the
exactly. So
pretext
if
of this?
you remember, I was talking about why we chose our loss function. So obviously the
Mhm.
simplest loss function is, you know, like negative lot, like cross entropy, or like maximum likelihood,
Mhm.
maximum likelihood estimation, right? We wanted to show, like, we did ablations on these loss functions. So empirically, like, what are the best loss functions? So for example, that bottom row and that grayed out row is the loss function we chose. So we trained different networks with different loss functions. So we tried out, all right, if we do cross entropy, like a maximum likely estimation, how good is it? So it it's okay, and does fine on some of them, but some of them it performs very poorly. If
Mhm.
you, for example, do maximum likelihood estimation plus our entropic regularization, it's not as good. If you do our method without the entropic regularization, which is the top row, which is any no entropy, it
Mhm.
doesn't do well at all. So we kind of ablate both parts of our loss function. So the
Mhm.
distance estimation part of the loss function seems to be an advantage over using cross entropy loss, or mean maximum likelihood estimation plus entropy. So there's
Mhm.
an advantage there. And removing the entropic regularization from a loss function seems to really hurt the results.
Mhm.
So both parts of our loss function seem to be critical for delivering good performance, which makes
Mhm.
sense, and we kind of hope this would be the case. And I think in this paper, we have graphs of what these distributions actually look like. So when you train a model with different loss functions, what do the resulting distributions look like?
Mhm.
I think if you scroll down, you could probably see that maybe a little bit. It's
Okay.
right below this, if I'm not wrong.
Yeah, that's the end of the paper. I don't know if they're included, but
Maybe I forgot them someplace. So, but suffice it to be
okay.
say, the cross entropy distribution, if you use just maximum likelihood estimation, the learned distributions are very spiky. It like puts a lot of
Mhm.
loss on a lot of probability on one single point, but on the other ones it doesn't put anything at all, right? If you do MLE plus entropy, it puts less, it's less spiky, but it kind of just uniformly raises everything, right? It doesn't have that distance metric. So it kind of treats every other bin the same. So it doesn't really
Mhm.
care about like the bins are close to our true answer or the bins are like far away from the bin true answer. It doesn't care. So
Mhm.
entropy, adding entropic correlation just kind of raises everything up. So it really doesn't make a big, really help that much.
How does it? Do you have a rationale for why it then outperforms regular MLE? Like
Yeah,
if
so
it just
Emily
raises
doesn't have
everything
that
up, it
distance.
seems.
Sorry.
Sorry.
Oh, I was gonna say Emily doesn't have that distance between bins built in, right?
Mhm.
Emily just tries to pick the bin with the highest probability, irrespective of other bins. Our
Mhm.
methodology says we want to put probability on bins that are closer to the true bin.
Okay. And so the way you're doing that is, as you said, by raising like a uniform distribution across the remaining states. And effectively, what we're saying is it's better to use a uniform distribution almost with a spike for one of these than it is to use simply a delta distribution that is only centered into
No,
one
so
bin.
no, sorry. I think there's a little bit of misunderstanding. So
Okay.
we don't learn like a uniform distribution. We learn a distribution where we put probability on higher near the true answer and probability lower near the out of the answer. So MLE,
Mhm.
for example, just MLE without interlocalization is just going to learn a delta function. It's going to put a lot of probability on one point and zero,
Yeah.
like very little everyone else, right?
Mhm.
MLE plus entropy does almost the same thing. So it learns, puts a lot of just probability on one point, but all the other bins are just slightly higher. They kind of
That's what
raise.
I'm saying. So that's what I'm saying. So MLE is essentially a delta function,
Yes.
and MLE plus E is well like a mix between a delta function and a uniform distribution.
Yes. We do
And
kind of a different thing, right? We learn an actual distribution over the things, over
yes,
the
yes, we'll get to that. But the point I'm trying to make, or the question I'm trying to ask, is if we're comparing this one to this one, and we're saying generally speaking, MLE plus E I think has better results, or maybe it doesn't actually. Maybe that was my misunderstanding in the beginning. So I thought we said that MLE plus E had better results than MLE. Uh,
Yeah, I think
because
they're kind of similar.
yeah, okay. Then that comparison doesn't make so much sense. My question would have been if MLE plus E has significantly better results, and the difference between these distributions is that in one of them we simply have like a delta distribution, and in the other one we have a mix between a delta and a uniform. It seems like just smearing this out without any knowledge of the right state anyway improves the performance. But that becomes, well, let's just toss that to the side because it actually does not perform MLE. So sorry, I'll let you go back.
Oh yeah, so I mean this kind of makes intuitive sense, right? If you just raise every other pin the same amount probability, you don't really improve. You're not really incorporating any extra information, right? There's no extra information
Right,
for you to form your set, so it's not going to do any better.
right.
Putting raising the nearby bins is much more informative.
Mhm.
So there's more information in that.
Yes. And that's essentially what we're doing in the actual loss function, right?
Yep, precisely.
And then for completeness, the reason why this one performs so poorly in comparison is that we get essentially delta functions there as well, or
Yeah, so it learns pretty close to delta functions, yeah.
okay, okay, very good. We should wrap up. So if there are any like conclusions about the paper that we didn't discuss yet, maybe other limitations that we haven't touched upon, or something you would like to conclude with, please feel free to raise it, and then after we'll wrap it up.
Yeah, I think the main thing is the point and kind of ethos of this paper is it's simple, right? It's just very simple. It's nothing fancy. The neural network that people use for a while apply to a problem. We just take the problem from a harder problem to something we've seen before and make it simple. I think, and we spend a lot of time trying to make sure everything is reproducible. So we have that pip library, that Python library that people, you can play with now. And if you have comments or feedback on that, please send it to us. We'll try to support any feature requests that you give or something reasonable. So we try to constantly improve our Python package, and we really want this method to be used. And from what I've heard, interacted with some people across industries, that this method is getting a little bit more traction in the fact that it's just very simple and very general hammer.
Mhm.
And so I think that's the kind of the key thing I want to get out of it. Like, please try and use this method if you are interested in this space. We hope it's very reproducible. We hope the ideas are very simple and kind of come clear.
Perfect. Let's wrap up there then. And for
Okay.
anyone interested, your contact details will be in the paper, and it's going to be linked in the description as well, so they can get in touch.
Yeah, that sounds so good.
Perfect. Thank you very much for joining.
Thank you. Thank you.